So having talked about the use case, ARM is pretty much the predominant architecture in the mobile phone world. Intel would like to change that in the near future, I guess. Over 15 billion chips have shipped to date, and 10 million chips of ARM are shipped every day. And this includes all kinds of embedded systems, not just smartphones in particular. And ARM is also looking to enter the server data center market in the future, and virtualization could be a benefit in that case as well, not just in the mobile phone world. So for the rest of the talk, I'll be focusing on ARM core virtualization, which can be used not only in our particular use case that we are targeting right now, but perhaps in the server data center market years down the line, if and when ARM enters the server market. So ARM's CPU state looks fairly straightforward. There's a bunch of general purpose registers. There are 16 general purpose registers that are labeled R0 through R15. The last three are actually called the stack pointer, the link register, and the program counter. There are primarily two privilege levels, one being system and one being user, or you can call them privileged and user. But the privilege mode itself, the privilege level itself, can actually house about 6 or 7 different modes, like the supervisor mode, the system mode, the abort mode, and so on. The different modes are basically, you can think of them as the modes that happen to be active whenever different kinds of exceptions occur. So for example, when a page fault occurs, in the ARM world, they're actually called data aborts and prefetch aborts. Whenever a data abort occurs, there's a data abort mode. Whenever there's a prefetch abort occurs, it goes into the same abort mode. Whenever there's an IRQ, for example, it goes into an IRQ mode upon a hardware interrupt, and so on. So all of these different modes comprise the privileged level of ARM's architecture. And of course, there's the user mode where all of the applications would run. Now notice that there are actually a couple of registers that are banked across these different modes. So for example, the supervisor mode gets its own stack pointer and link register. The abort mode gets its own stack pointer and link register. There's one mode called the FIQ mode, which stands for the fast interrupts mode, which actually gets a few more of its own banked registers to improve performance while switching to and from its mode. So the idea here is, because you have these registers independent, you do not have to save those registers of the mode from which you switched. And then you have some special registers called the processor status register. Specifically, there's the current processor status register called the CPSR. And then for each mode, it gets its own saved processor status register, which is the SPSR. The process status register itself, I'll go into a little more detail in the next slide. It contains a lot of mode bits and current enable, disable bits, and so on. And every time an exception occurs, whenever the hardware switches into that exception mode, it actually saves the current process status register's value onto that SPSR, onto the appropriate SPSR. For example, when you're switching into abort mode, the hardware would save the CPSR into CPSR ABT, and so on. And of course, in addition to the general purpose registers and the process status registers, ARM actually has a bunch of co-processor registers, including for control registers like the page table base and paging enable and disable and so on, as well as for floating point and all sorts of other registers. So let's zoom into one particular register, which is the CPSR, the current process status register. The CPSR itself, actually, if you look at ARM's own manual, looks fairly straightforward. It seems to have some fairly innocuous bits from our perspective, from virtualization perspective, like the 0 flag, the carry flag, and so on. But it also has a bunch of privileged state, like, for example, it actually has interrupt enable disable, which is the I bit on the right. It also has the current mode of execution, which sits in the least significant bits, which basically says, are we in user mode, are we in abort mode, are we in supervisor mode, and so on and so forth. Notice that it actually, this register actually has some bits that are sort of harmless and innocuous as far as virtualization is concerned, and some bits that are of not only of relevance, but very important to the virtualization layer itself. This is very similar to how the E-flags register on the x86 architecture itself is mixed in terms of having both privileged and non-privileged state in the same register, which leads to several problems from a virtualization perspective. So I'm not going into too much detail about the rest of the bits, but the important thing to note here is that the virtual machine monitor's interest is in only some of the bits. And the important thing to note here is the ARM architecture actually is not strictly virtualizable, primarily because one of the primary reasons being the CPSR register. So remember that I told you one of the requirements for strict virtualizability is that all instructions must either, all privileged state access instructions must either trap, or all instructions must either trap or execute identically in both privileged and unprivileged modes. In this case, what happens is a write to the CPSR, whenever you rewrite the CPSR register from a privileged mode, the hardware actually rewrites all of the bits. So let's say you're in supervisor mode and you rewrite the CPSR register. It actually rewrites all of the bits. Let's say you're in user mode and you rewrite the CPSR register. The hardware definitely does not rewrite the mode bits or the interrupt enable bits, as you can imagine, because you do not want the user mode to be able to arbitrarily switch to supervisor mode to do some bad things, for example, or arbitrarily disable interrupts on the underlying hardware, for example. And therefore, it actually sort of masks out those bits and only rewrites the other bits that the user mode is actually allowed to rewrite, like the 0 flag and the carry flag and so on. And because you have this one instruction, the write to CPSR, for example, behaving one way in one mode, the user mode, and behaving in another way in another mode, the privileged mode, you actually have the strict virtualizability requirement being violated right there. So this is sort of one specific instantiation of the violation of the strict virtualizability on the ARM architecture. Very similar to how x86 has the rewrite of the E-flags register, the popf instruction, for example, behaving in different ways in different modes. So given that there are these sensitive instructions that happen to behave different ways in different modes, how do we deal with them? Well, as I have explained in my previous talk, you have an array of options, starting from interpretation all the way to hardware-assisted virtualization, to deal with these sensitive instructions. Within MVP, we decided to choose one point in this space, which is the shallow para-virtualization, where you end up replacing all of the sensitive instructions with either their emulation implementations themselves or with hypercalls to actually do more sophisticated emulations from within the virtual machine monitor. Now, the reason we chose this is because para-virtualization itself simply requires modification to these sensitive instructions within the source of the guest operating system. All of the guest applications, of course, still remain unmodified. Only the guest operating system kernel needs this set of modifications. And in our case, we found that, in our use case, we found that modifying the source of the guest OS is not such a big deal for us because of the deployment model in the mobile phone world. Now, remember that in the desktop world, you buy an operating system, let's say on a CD, or download an operating system or something like that. And on your laptop, you can, out of your own whim, decide to install Windows or Linux or whatever have you. And you as a user get to do that. But in the mobile phone world, typically the entire ecosystem, the OEMs, the manufacturers of the phones themselves, the carriers that provide you the mobile phone voice and data services, all of these people actually control what kind of operating system gets installed on your mobile phone, what kind of access permissions different applications get to different devices on the underlying hardware, and so on. And because of the deployment model, you actually need to anyway go through the OEMs and the carriers to actually make a given mobile phone end up with a given operating system as its virtual machine and so on. And because we have to anyway go through these ecosystem players like the OEM in the enterprise, and because we ourselves are actually providing even the guest OS instance. So for example, in our MVP solution, we actually do not give just the monitor itself, the virtual machine monitor and the virtualization layer itself, but we also provide the work phone, the virtual work phone, as part of our solution. We also have another management solution and all of that, which is not relevant to our talk here. But because we are actually packaging the guest OS along with the virtual machine monitor layer, the guest OS is pretty much in our control in terms of being able to make modifications and so on. Given that making modifications is very feasible and very much part of the process and acceptable, we found that going the para-virtualization route would be the easiest way. Of course, at a future point of time, once ARM's hardware-assisted virtualization actually comes out in the market as available chips in the market, we will obviously be looking at other options as well. But
do you have an iPhone product then?
No, as of now we do not. We target only the Android phones. So we actually have Android virtual machines running on top of Android physical phones. There's obviously no technical reason why you couldn't do virtualization on an iPhone. It again runs ARM architecture. But the problem there is, in order to run a virtualization layer on the underlying hardware, you need some sort of a kernel module or kernel access in order to be able to sort of take control of the overall hardware, take control of the world, so that you're able to enforce isolation and do all of these other virtualization implementations. And because we require guest kernel access, sorry, not guest, because we require kernel access on the host, on the underlying hardware, we actually need to go through the OEMs and the carriers and so on. And we have actually set up partnerships in place with OEMs and carriers to be able to do this in the Android case, but not yet in the iPhone case at least.